So today, I'm very happy to present to you our first speaker, Ola Aarøen. I did it wrong. We just discussed it. Aarøen. But he's from the Institute of Biotechnology and Material Tech.
Food science.
Food science.
Yeah.
I had to translate on the fly. And today he'll be talking about interactive plotting using Python and Matplotlib. And the focus will be to show you some cool things that he eventually did with illustrating Monte-Carlo algorithms, which is some pretty cool stuff. So I guess I should let Ola speak now.
No, thank you, Brian.
Yeah.
So just first off, on the webpage, it's the title's just saying interactive illustration of Monte-Carlo algorithms. That's just a bit of an error. We have to do a bit of the interactive Python and Matplotlib until we can get to that point. So yeah, just a small disclaimer of that. So yeah. Also, I just want to make it clear that my Python is self-taught. I've already, somebody in the audience pointed out a small error in some of the code. It's what I, as I write here, it's learning by burning, basically. I try it out. If it works, then yeah, good. I had to learn this doing a project for a professor at the Department of Chemistry called Titus van Erp on the illustration of these Monte-Carlo algorithms. And before that, I didn't really know much Python plotting. So yeah, this is mostly self-taught. I should also give some acknowledgements to Anders Leivik, postdoc for Titus van Erp, because he has done a lot of work on the illustrations of these algorithms in the past, and I've proceeded on this work and trying to make it more interactive. The content that I'm showing you today is mostly based on the online examples that can be found here. My text is sort of wrong, okay. And the examples I might get back to later, depending on time, is from the Pyretis library, which is a rare event simulation program developed by the group of Titus van Erp. So just basically what we're going to go through today. I'm going to give you a short motivation for Python and Matplotlib. I'm going to show you examples using the interactive tools that exists. I'm also going to show you examples on animation using Matplotlib, which is also a feature, because I'll use it later on. So I'm just showing you this so that you see at least what it is before, like, oh yes, it is moving. I'll also do some small parts on graphical user interface, because that's also something that I've used for this project. And then again, depending on time, we'll get back to the main examples from the Pyretis library, which describes the Monte-Carlo algorithms, and this analysis tool that I made using interactivity and graphical user interfaces. So, why use Python or Matplotlib? Well, being self-taught, I can say that it's really easy to learn. It's made to be easy. And if you can install Python on something, it can probably run it. The advantages of Python over, for instance, MATLAB is that Python you can write object-oriented code. This will come back when you're doing some more advanced interactivity, because then all of a sudden you have to create your own objects to give them functionalities, say creating a figure and adding buttons and such. It's also, Python in general is also a program preferred by most large companies, because it's easy and can almost solve every task you throw at it. The package Matplotlib, which is a sub-package of the main Python build, offers figures of, well, arguably publicational quality. It sort of emulates MATLAB, so it should look the same, and operate the same, so that the transition from MATLAB to Matplotlib shouldn't be that hard. And you can also have the option to output directly to LaTeX and TeX files, so that you can quite easily import it into your articles. And most of all, the main plotting, or like the basic plotting of Matplotlib, is mostly single code. If you want a bar plot, you do plot bar of something. You don't have to set up a lot of stuff as you else would in, for instance, MATLAB. However, there are also some cons to using Python. As it is a scripting language, it will be relatively much slower to others, such as C or Fortran. It's quite memory intensive. You don't allocate your memory at the beginning, so you just keep adding on stuff. And this again will track back to it being slow. The multiprocessing or parallel programming part of Python is really, really bad. It exists, but it's hard to do. I tried some using in the GUI I'm coming back to, but it's not perfect. And Matplotlib in general is really not great with 3D objects. If you're trying to print, say, a 3D surface, you'll get these weird, what's it called? I'm forgetting the words, but it's the object will look it will look almost transparent, so you can see stuff that's behind, in front of. Yeah, it looks weird. Just it's a good word for it, but I don't get it right now. But still, why choose Python? And the reason I think is best summarized using just one picture from a simple webcomic, which is this, where it's the webcomic XKCD, for those who don't know. Basically, he's saying, oh, how can you fly? Oh, I've imported anti-gravity. That's mostly how Python works. If you need something, yeah, there's probably a package for it, and you can import it and use it. So it's really user-friendly that way. That's why I suggest that you use it. So onto the meat of it all, the interactive plotting. Now, what do I mean when I say interactive plotting? Well, instead of just showing a figure, you can give some functionalities to it. You can say that, okay, I have a button that will perhaps calculate the analytical derivative of my data and plot it, for instance. Or maybe there's a slider that gives me opacity so I can see stuff behind it, or stuff like that. It's basically things that you can do on the fly, which if you had to write it in a terminal would take you considerably longer time than if you just had this pre-written as a script. So you'll be adding buttons, you'll be connecting events to certain functions, etc. And then when you load your data and put it all into this, you can sort of operate your figure a bit more than just showing it or saving it. And yeah, and you can also have functions that will sort of change your data, or or as I said, calculate analytical derivatives, or I'll show later some regression lines and such, just for instance, that you can use. And all of these examples will be based around the same basic plot that I will refer back to. So you can see just from this basic plot, okay, what are the new imports that I've used? What new functions have I created to make this new example? So just first this basic Python plot, which looks something like this. Here I use a precompiled data file called data.txt. I've just opened it. I've read the number of lines or number of columns of data. I've read all the data in. I've specified that these are floating numbers. I set up my figure. I plot the data. I'm sort of cheating here because I know that the first data column is the x-axis values. So I plot all the data to the x-axis values, and then I get this figure. which is basically the x values, x squared, x cubed, sine, cosine, and exponential functions. Now, taking this example and expanding on, we can add buttons. Let's see. Okay. Yeah. First of all, and now I'm using a different data file now because just working with these x squared and x cubed values became a bit boring. So I've used data from an optical tweezer for spectroscopy instrument that I'm using in, as part of my PhD in biotechnology. And then we get a data file that looks like a plot that looks like this instead. So this is basically it's the forces in x, y, and z direction and the sum when pulling two, I think it's oil droplets apart using the optical tweezers. So you'll see you're pulling them apart, and the forces are well resisting the pull, and at some point they release, and then you see this drop off of energy here. So this is just the data I'm going to be using. So get used to this data, these plots, because they're going to appear again. So yeah. So first, I'm going to add a button to this. And what I do first is I have to import, as always, import from Matplotlib widgets the function that's called buttons. Everything else here stays the same. I'm still loading the data. I'm still setting up my figure. But here, I have to create two additional objects. I have to create two additional axes of the plot. Axes are stuff that you can basically, that's places that you can plot your data into. As you can see here, I have my main axis here, which I will plot the data into. And here I have two axes that I will call button and reset button, or plot button and reset button. And using this function, I just turn them into buttons. And I assign to them two functions. One function is the same as before, it just plots the data. But in the previous case, it did this automatically, so you didn't see it. And the other one just clears the main axis. So it removes everything that's plotted in there. I connect them to the buttons, and I show the figure. So when I run this, the data shouldn't plot. You should see two buttons and a blank canvas. And this you do. So you have two buttons here. You have plot and reset. Now if I hit plot, it should plot all my data. And it did. And if I hit reset, it should clear my axis, which it did. And I can do this again and again. But this is just a very basic example. You can assign more advanced functions to this than just plotting and replotting. So that was the normal buttons, which I call them. You also have something called radio buttons. If you've ever filled in some sort of online form or survey or something, you've encountered these. These are a set of buttons that where only one of them can have the switched on value, and when you press the switch on value of one of them, it will turn the others off. So it's like choose one case. Again, it's an import, and again, I have to create an axis and assign this axis as, yes, these are my radio buttons. However, now I also have to give them names because they have to make sense. You have to know what's the button that I'm pressing. Last time it was just plot and reset. So now I've assigned them as vec because it's the sum of the vector components, and x, y, and z. And as you can see, I'm still plotting my data, but I'm plotting it with the visibility of false. So this will plot, but it will not show. The object is there, but it's hidden. And to my function, I have given given it so that when a button is pressed, it will make the correspondent data stream visible. So at any time, I can only show one set of data, which I showed you in the previous one. So if I now run this, I will get this figure, where I have my radio buttons and the currently showing data stream. Now it's showing the vector sum. If I want to see the x, I press and it updates. The y, it updates. Go back again. The data is all there. It's not shown, but it's plotted. So it's different from the previous script because that one deleted the graphs when we pressed it. But this is just playing with this hidden functionality of them. And carrying on from radio buttons, we have, of course, check buttons because, well, maybe I want to show more than just one. And it's almost completely the same, except that I import check buttons instead of radio buttons. It's still names. I now have to keep track of a list with Boolean values because when first drawing this figure, I have to know, okay, is some of these turned on or off? So in the beginning, I'll just say that, oh yeah, they're all off. Show me nothing, just show me blank canvas and buttons. And this will give you this, which looks a bit different and operates a bit different because you can have multiple turned on at the same time. And you also have the possibility of having none of them turned on at the same time, which is not a possibility with radio buttons. They will actually, if you just generate radio buttons, they will default to having the first option always on if you not specify this. Now, we're going to go over to something called events, or I'll combine them all into what I call events. And these are not something that you strictly have to import from somewhere. They are not like the buttons. You don't have to import the function. They are mostly built into the canvas, the actual plotting area of your figure. But you just have to know how to access them. For instance, you can access them by clicking, which is here I have created a function that will say on the event of clicking on a plot or picking something on a plot, I will do this, which is, give me the x and y data of whatever I've picked and set it to the title of the plot. And also, in order to be able to pick these, I've just changed the, it's not plotted in lines anymore, it's plotted with dots. So it should be easier to pick a value. So if I now pick a value, it will display on the title. So, but if they are grouped close together, because there's a tolerance on picking points, you'll see you'll get more values than just one. So that was one type of event. We have more that we can concern as moving events, because at every time when you're moving the cursor in the figure, it actually keeps track of where your cursor is at. You will actually see it on the bottom of the figure. You'd see the x and y coordinates of your cursor at that moment. But if you wanted something more visually on that, say for instance in this plot, okay, I'm picking points, but it's hard to see which point am I picking. We could use something called cursor, which just generates sort of a crosshair following the cursor around in the plot. And it's set up pretty easy. You just say, oh, I want a cursor on the given axis. I want this useBlit function to be true, because blitting is basically saying that, okay, when you redraw something, this we'll get back to this in animation. When you redraw something, just redraw whatever's been changed. It will save you a lot of memory later on. Yeah, so this is, oh, you almost saw it there. So now you have a cursor following your pointer. So if it were difficult to pick your points, then maybe now it's easier. Or you can see, just using the cursor, you can see what are my x and y values, even though you can see them at the bottom of the screen here as well. You also have the option of something called a multi-cursor. This works almost the same as the basic cursor, but it works on, well, yeah, multiple axis objects. So here, instead of plotting all my data in the same axis, I've created 4 underneath each other, plotted the data, and say that, okay, I want a multi-cursor on this. So I have a multi-cursor that follows the pointer in all the axes. So that's also something you can do. If we want to combine these by using both the events of clicking and moving, we can start to get inventive and draw things. So this is something that should draw vectors for me. Now I have two events here. I've button press event and button release event. So something happens when I press the mouse, and something happens when I release it. So when I press it, I store x and y values. And when I release it, I store the new x and y values, and I draw a vector from the original to the end. So say that I have my data here, and I was like, oh, I want to point out this outlying data value here or something. I can just press somewhere else in the plot, I drag to, and release. And it draws an arrow. Or you can do it like here, or there. Well. So that's also something. And yeah, you can see here that I have the two functions that govern this, that are start of my vector and end of my vector. And I use this built-in quiver plot, which is mostly used for displaying electrical fields and such. But you can use it also to make vectors in Pyplot. I think there's one more. No, that's okay. Now these next one, draggable objects. Well, they mostly they could be described also as these click and move and release things, but I've sort of separated them from the rest. This is again something that you click, move, release on the plot. You have a couple of built-in ones that are quite useful for something. You have, for instance, what's called a span selector, which you can use to select part of your axis and do something with. The original case online was really boring because it was used to zoom in on a part of some, looked like a spectrum of something, which is really stupid because you already have a built-in zoom function in the figure, which is better. So I figured instead, okay, I can make a linear regression using the span selector. So you can do a linear regression on a certain given span of this data that I have. So again, you can see, yeah, just import here. Here it's just a function making the regression line, and a legend, so you can see the actual function of the regression line. And the span selector is just set up by calling this function. Again, use split true. Now, okay, so here's my data. So say that, okay, clearly this peak is interesting, and I want to see what's the slope of this peak. Well, yeah, I can click and drag, and you'll see this span appearing from beginning to end, and this will track the XY values of start and end. Or in this case, it will track the X values of start and end, and I can use that to get my X and Y data and calculate the regression line. I don't know, do you see this? Is it really? Yeah. And then you get the regression line from this. And you can do it here, or maybe you want to do the entire thing, and you can see, oh, yeah. So if you wanted a tool that you can, okay, I want to really inspect just this part of the data, but I'm too lazy to remove the parts that are uninteresting, or I don't know where the uninteresting parts appear before actually plotting it and seeing it. Here you have a tool that you can do this with. Another built-in thing is what's called a slider. And I talked about this in the beginning, that you can use it to change the opacity of stuff. Basically, a slider is something that you have a start and end value, and you have a point in between. You can move back and forth and set some numerical value, and this can give meaning to your plot. So here I have set up two sliders. I have one doing just transparency of a graph, and one doing what I call box length, because I'm doing a moving average here, and I just want to set the box length of this moving average of the data. So yeah, I've imported slider and button. I'm also making a reset button here, just to reset back to original values, but not to worry about that. Okay. So as you can see here, this is changing the opacity on the fly of this orange graph. So yeah, okay, we really want to see this. And this orange line is now the moving average line of my data. And I can adjust the length of the box using this. And you'll see as moving averages go, when you increase the box length, you lose a certain amount of data, because of course you're losing it when you're averaging. And then you can create, and you can, well, yeah, analyze this on the fly. This has already been analyzed once, the blue data in the background, so it might not be as effective as it should be, but yeah, you can see that it's doing something on the fly. It's calculating something and it's plotting it. And in this case, it was this running mean function that gives you the moving average, depending on your data and your box length here. Now, these were both built-in cases. I just imported them. Also, you can create your own. Now, this code gets a bit messy because, well, you've created your own object. Here again, you can see the why Python is so better, because you can have object-oriented programming. Here I've created an object, which I call a draggable circle. And of course, this circle has the function that, yeah, you can drag it. You can click on it, you can drag it, you release it, and it stays in put. And I'm just plotting my data, and I'm turning all the data points into this draggable circle. One drawback of this is that since it's a circle object, it has to have an equal aspect ratio. So my plot now looks a bit like this, but I can zoom in instead, so you can get a better view of this. I've taken a small part of it, and now you have objects that you can move. You'll see all of this used later. This is just now for illustrative purposes. Okay, now we're going to go a bit of a detour, and we're going to focus on animations, because those are also a possibility. Key feature of them is, of course, yeah, you have to import something again. You have to be, when doing animations, you also have to be careful using blitting and artist objects, because in order to make this as efficient as possible, you have to know, okay, which parts are moving, which parts are staying still, so that I know that with yes, these parts I have to redraw, and these can just stay put. It's also a function that you just start and it runs on its own, almost like a while loop or a for loop. So it's more difficult to make this interactive. You can make the interactive part before, then start the animation, maybe at the end to do something more. But while it's running, it's very difficult to do anything. Because, as again I said, Python is not very good at parallel programming. So it's difficult to do things at the same time. If the plot is concerned with, okay, I'm doing this animation part, it's going to be difficult to do anything else in the meantime. Nice things also with the animation function is that you get the option to store it. You can store it as a video file or as a GIF, so it's easy to use later for illustrative purposes. You don't have to run the entire code again and again. The two examples that are just lifted from the web page here are what's called the decaying sine wave and the dynamic image. They both are fairly short code-wise. Worth noting here is that you have this func animation, which runs the whole thing. This just starts and goes. A couple of inputs you have to input the figure so it knows what figure am I animating. You also need a couple of functions to sort of change your data or change whatever object is shown. Again, blit true, very important option. You also get some options there on how many frames per second. I think this interval is millisecond per image, I think. Also get the option to repeat if you want to. And this init function, which is just, what's my starting out, basically. So if we run this, you'll see here. So, okay, worth noting there, I just enlarged the image, so I lost a couple of the data. This is, it's not a perfect function, but it sort of works. I mean, if you're going to make small and easy examples, this will do your job for you. But you can see there are a couple of glaring errors here. For instance, where's my x sticks? Where's my x values? And the truth is, you don't get them. They are outside of the axis object, so they don't get updated. Everything updated is within here. So yeah, it's not perfect. I mean, it works and it can look cool, but if you really look at it, it's not perfect. Yeah. And yeah, and a different case here is the dynamic image, even less of a code. This is I use this just to show that, okay, I can save this as a GIF or a video file, because I did this also. You can see here this video file, which shows, the same thing. And it's really easy to make them into video. You just have to uncomment these two lines and comment this one out, so it doesn't show the figure, but instead saves it as a video, or in this case, a GIF. Okay, just a bit on graphical user interface, because it's going to be really short. They are basically what you use to make the windows that you see on your screen. So when you see something that has close, minimize buttons, and they appear as programs, these are graphical user interfaces. It's not working in the terminal. You have a bunch of them. The Matplotlib figures are based on this tkinter thing. You have a bunch of others that are very easy to install, either by pip or homebrew or conda or whatever. You will notice if you're using something like Avogadro or JMol or whatever, you're familiar perhaps with OpenGL, which is mostly used when trying to show 3D objects. In my case, I used Qt, which I found really easy. It's based on C++ code, and you interface it to Python using, again, an import package called pipeqt. And you get, windows that look like this. And it's really easy, and I'm actually going to just show you how some of these are made. So if I now, if I open just, so I want to make a main window. Oh, I'd have to save it somewhere. Okay, I'll do a recent then. Okay. So this is a GUI I made for the Paretis program of Titus van Erp. So this is really easy. You have a main figure that you at any point can just click and drag and add buttons to. Say I want some push button here. Okay, I have a push button there. Oh, I want let's see how it's. I want this to be a vertical layout instead of a horizontal layout. Okay, I can do that. You have a lot of options here of just dragging and dropping and adding stuff to your GUI, making this .ui file that you then can import in your Python script, and it will create this window. You also have the option here of doing signaling and slotting and connecting events. So, for instance, I want my exit button to actually close the window. You can do this here. Or I want my analyze results button to open another window. You can do that as well. So it's really easy to use and just create a small program for whatever you need. Okay. Nice part also is that it's easy to include external components. So in my case, I included a Matplotlib figure into one of these GUIs because I wanted to plot something and make it really, really interactive using a GUI instead of this tkinter interface that's native to Matplotlib. And this is it. And if I just open this. So, yeah, as you can see here, this is a Qt GUI with an embedded figure canvas from Matplotlib. I'm using this to visualize data from a simulation done by one of the postdocs of Titus van Erp. And if I just find the file here. Okay, we'll do this one. Okay. So, okay. So that's also nice. You can make like really fancy looking programs using this. So this is a program just showing the outputs of a rare event algorithm simulation, a Retis simulation. And the output gives you a lot of data in a lot of folders. And you also have a bunch of descriptors or values to your data that you might want to show. You have some cycles, perhaps. Maybe there's a shift in the data, whatever, and resolution and stuff. And you can create figures. This, okay, didn't look good. Maybe if I decrease the resolution, you should see bigger blots. Yeah, like this. And yeah, this is a really easy case because it's just you have two descriptors here. You don't have any else. But say that you had 13 and you wanted to see, okay, which ones correspond most, or which ones prove to lead me into sort of a metastable state that I don't want to be in. You can use this tool to plot them against each other on the fly and see that, okay, this one gives a bad result, this combination gives a good result, and so on. And again, also added some small features here of turning on these phase-space interfaces that are used to describe different ensembles of the simulation. Data shift, as I said, because if you have values that are, if your descriptors are angular based, then you know you'll wrap around when you get to minus 180. You'll wrap around to 180. Then you can do this with the data shift. You also have a bunch of different plots here if you want to show. Oh yeah, I want a scatter plot of this, and I want to see the potential energy of it. Yeah, then you get something like this. Or nah, I don't like this color map. I want to try something like jet. And that really didn't do anything. Oh, that's bad. Okay, so it seems to be broken. Okay, never mind. Okay, then it's updated. Yeah, so this is just a tool that I made for him to inspect the output of a simulation, and yeah, I'm really proud of it. And I've used at least some of the techniques that I've showed you using this. Now, on to well, I don't know, how are we for time? I mean, I can show a couple of examples.
Yeah, just a couple of examples.
Let's see. So this is another GUI that I made. This is, as you can see here, it's part efficiency, part laziness, because these are examples in subdirectories of subdirectories of subdirectories lying around in this huge Git folder. And I got tired of having to navigate back and forth to run them and test them. So instead, I made a GUI that just knows, okay, well, yeah, my simple pendulum case is in this folder, so yeah, I'll run it from here. So you just have to run this one program, and then you can execute all your examples from here. The nice thing also is that it calls them back end. So if I do a change in the code while still having this window open, it won't get stuck with the old version, because this will call the example as you would in a terminal, if that makes sense to you. So, for instance, some of the examples that Anders Leivik made is this, where you have combined animation and an integrator of motion and a potential from the Pyretis package to simulate a double pendulum swinging with the outputs of kinetic, potential, and total energy over time. So some things I did to make this more interactive for students perhaps was to see, okay, what's a different in time step going to do to this simulation? So yeah, I made some buttons here that will update the time step of 2 different pendulums. So if we say 32, okay, so now we have one pendulum running at 8 times the speed of the other, essentially. And then you can start the simulation. This is really slow because it has to, calculate and draw 2 pendulums at once. And you probably won't even see it, but there's actually 2 here. They're just overlapping, but yeah. Okay, that's really not good. Anyways. To go back to, for instance, the clickable, the draggable objects that I made, is this case where we have a 2D MD simulation, again using integrator and potential from the Pyretis package. However, I made it into 2 systems put on top of each other using different initial positions and making one of the systems movable using this draggable object that I showed you earlier, so that I can move this red system. The blue one is fixed. You can't do anything with it. But you can move the red system, and at some point you can say, okay, now I want to execute the MD simulation, and it will run for both cases. So you'll have the blue system beneath running as one system. You'll have the red system running as one. So the idea here is that you could have students running this example and teaching them that, okay, how to see how chaos in the system will work over time. So you could, if I didn't do it so extreme as I did there, but if I did sort of like move this a bit and play, so you have a small change from one system, you should see a larger change over time as the system progress. And yeah, you'll see that more and more of these particles differ in location at the same time from the original system that is underneath. And to the actual Monte Carlo moves, I try to illustrate how the Monte Carlo shooting move works on, both on a free potential and on trajectory from a transition interface sampling simulation. And depending on how much you know of transition path sampling or transition interface sampling, this might not make much of a sense to you, but basically here we have a particle in a 2-dimensional potential surface. It has moved from this well out and back, indicated by a red and a green line. And these round spots here is objects that are made on this line that are clickable. And by clicking on the object, you will perform what's called a shooting move. You'll take the position of that point, or the position of the particle at that point, and give it a random velocity from a Boltzmann distribution, and do another, or make another trajectory using these new speeds going forward and backwards in time. So as you can see, I clicked and I generated a new path. And if I click this new path, it's also interactive, or this new path is also interactive, and so on and so on. And the thing here is that you can get students to see that, okay, how are shooting moves done, how that by clicking on this path, you create a new path, which is basically how the Monte Carlo move works. And also, as a goal, you can have them trying to reach the end state here by just doing this clicking on and on and on, because that's essentially how the initialization of a simulation would work. that you had to reach the end or pass the last interface at some point to before you actually start the simulation. So it's sort of twofold what it would do. But yeah. And the final one I made is this, I think. Yeah. So this is a combination of an example that Anders Leivik made, and I tried to make it a bit more interactive. Thing here is that you have a particle in a one-dimensional well. You want it to cross over, and you want to calculate the crossing probability using the radius algorithm. But for the radius algorithm to work, you have to add interfaces to calculate the crossing probability from the previous to the next. And this can be done interactive using, well, you recognize the multi-cursor, and you'll see that clickable objects by clicking and drawing interfaces along this energy curve here. And when you're satisfied with interfaces, press play. This should close and open a new window. I don't know if it's been, there's been an update, it might not. Yeah, and then your simulation runs, and it draws the paths and flux and probability on the fly. So just a short animated example of how does the algorithm or the program underneath, how does it work? How does it run? Yeah. And there are a bunch more here, but yeah, I don't really think I have the time, or I have to give each other. And yeah, just conclusion here. I find Python very easy and very modifiable and quick to use. And as I said, there really is a package for everything. And if you encounter an issue, be sure to know that somebody somewhere has encountered that issue before and probably has asked the same question on Stack Overflow. Yeah. Why use animation? Well, yeah, moving picture. A picture may be worth 1,000 words, an animated one might be worth a bit more. I don't know. I like to think that I've shown you at least that interactivity could be useful to, maybe not all the examples, but one or two of them could be useful in your own research to use. And yeah, you're only limited by what you can imagine doing with them. I didn't think of this regression line thing until after we talked about how useless the original span selector was. So yeah, yeah,
Excellent.
that's